please.
Can you see the slides? Yes.
We can.
Okay, thank you. So this is a joint talk, a joint work with Dario Della Monica, Salvatore Latorre, and Angelo Montanari. We are talking about planning, and in particular timeline-based planning. So you may know from literature many planning languages such as PDDL or STRIPS. And these are all action-based languages in the sense that you model your problem with some actions that are executed by the agent, and when you execute an action, you have some effects that affect your state and so on. Instead, here we are talking about a different approach, which is timeline-based planning, which is an approach that is mostly focused on temporal reasoning. And the major difference is between this approach and the action-based approaches is that there is no clear separation between actions and the states that are affected by the actions and the goals, but rather we have declarative settings where planning problems are modeled as systems made of a number of components. These components are independent but are interacting in some ways. We represent the components of the system by some state variables, and the timelines, which give the name to the paradigm, are the description of the behavior of these state variables over time. And the evolution of the system is governed by a set of constraints, which are temporal constraints, which are called synchronization rules that define the problem. So instead of having the description of the actions and the goal, we have some temporal constraints that have to be satisfied by the evolution of the system. So this kind of planning languages really shine when you are modeling and reasoning about a system that is made of many components rather than the behavior of a single agent. So if you are planning about, we will see a couple of examples, but if you have a complex system and you want to reason about the behavior of a complex system, then this kind of languages really shine. And this is also an approach that is quite tailored to temporal reasoning. And it's also an approach that has been developed from the start with an eye in integrating temporal planning with execution of the plan. We are not going into much details about this topic in this talk, but this is one of the key features of the approach. So where does this approach come from? It comes from a number of applications developed mostly in the space sector. So we have mostly work from NASA and the European Space Agency working on the planning systems used to do onboard planning for onboard autonomy of spacecrafts and on-ground planning for short to long-term mission planning and scientific planning of the scientific activities of the spacecrafts. So this is the kind of applications that you can have in mind. So I have a little example of how this kind of planning problems can look like. So suppose you are planning the behavior of a spacecraft that is orbiting Mars, and you can this spacecraft can be in 3 different pointing directions. So we can point to Mars, or we can be slewing towards the other direction, or it can be pointing toward Earth. So we have these 3 kind of pointing directions. Then we have 4 activities. We can be doing scientific measurements. So we are pointing towards Mars and we are doing some scientific measurement, or we are communicating data to Earth, or we are doing internal maintenance, or we are idling, waiting for instructions. And you may want to apply some temporal constraints over this kind of pointing modes and activities. For example, you want scientific measurement to be done only when pointing to Mars, and you want communication to happen only when pointing to Earth, and only when a scientific receiving some ground station is visible. And you may want to apply to reach some goals that are not distinct from other kinds of constraints, but you may think them as goals. So for example, to perform at least a given number of scientific measurements in a certain amount of time. Okay, so I'll show you then an example of how this kind of setting can be expressed in a timeline-based language. So the state variables are the core of the language, and they describe the components of the system that we are going to reason about. So a state variable has a domain, which is a finite set of values, a transition function, which is similar to the transition function of a deterministic, non-deterministic automaton. So we have a function that says which kind of values can follow a given one. And then the duration function, which says the minimum and the maximum duration of a contiguous interval when a variable has a certain value. Okay. Here we assume that the temporal domain underlying our problems is discrete, but there's work on the dense settings as well. So these are the state variables. And this is an example of temporal evolution of a timeline-based system. So these are three timelines for free variables. So we have a variable for the pointing direction that is going through different values. We're pointing over Earth, we're zooming, pointing to Mars, etc. The variable for the activity, which is idling, doing scientific measurements, and so on. And the value for the variable for the visibility of the ground station, which is visible or not visible. Okay, and this is a bit of terminology. These contiguous intervals where the variable holds a single value are called tokens and are the core object that we are talking about in the constraints that I will show you in a moment. So this is an example of a synchronization rule, an example of a constraint that we are using to express our goals. So it says for each token where the variable xa equals to science, so for each interval where we are doing scientific measurement, then there exists another token where xp is equal to Mars, so we are pointing to Mars, such that A is contained in B. And so we can express the relationships between the endpoints of the tokens in this way. So this is the kind of constraints that we can apply to the system. The general syntax is this one. So we can have this junction of existential blocks of this way, of this kind, or with a universally quantified trigger. So this universally quantified head is called trigger. Okay. So the general syntax of the temporal relationship that we can apply that we can use in the constraints allow for a lower bound and an upper bound to the distance between the two endpoints. And in this general setting, the problem is X-space complete. So this is previous work, and we know that the problem is X-space complete in the general setting. But this high complexity makes us wonder why such a complex problem can be solved in practice very well in all the real world examples that we saw previously. So makes us wonder whether simple fragments exist. And so in this paper, we worked on the complexity of qualitative timeline-based planning problems. So problems where you cannot have a general lower and upper bounds here in the temporal constraints, but you only have constraints of this kind. So when you don't have lower nor upper bounds to the distance between the endpoints, and you don't have upper bounds on the token's duration. So the main result of the paper is to show that qualitative timeline-based planning is p-space complete as opposed to the x-space completeness of the general problem. And I'll give you briefly an idea of the proof. It's based on automaton construction. So we encode a given timeline-based planning problem into an automaton and into a non-deterministic finite automaton that accepts a plan, the word representing a plan if and only if the plan is a solution for the problem. The size is turns out to be exponential, and so we can solve reachability on the fly and have the p-space upper bound. And the automaton construction is based on a key concept, is that the concept of blueprint, which I will explain to you quickly. So this is an example rule for each token where xp equals to vb. We have two tokens A and C with the corresponding values, such that B is during A. So this is a shortcut to say B is contained in A and C is contained in A. Okay, and this is a possible set of timelines that satisfy this rule, and it's satisfied in two different ways. So you see that this rule is triggered twice here. So it's triggered by this token and by this one. And in both cases, the rule is satisfied. So this is a graphical representation of the rule. And if we also add some other kinds of nodes here, that this is what we call the blueprint of the rule. So we have nodes representing the endpoints of the intervals, and nodes that are the square nodes that we call the pumping points that represent the points in time where the automaton stops after reading some letter of the word. Now it will be clear later. So I'm picturing two copies of the same blueprint for a reason that will be clear immediately. So let's suppose that we are reading a word that is representing these three timelines. So we start by reading the first three events here, the start of these three tokens, and here we are pointing to the first pumping points. Okay, a blueprint together with a set of its pumping points is called a viewpoint. So a viewpoint is a pointer to which place in the blueprint we are right now when reading a word. So here we can go on and reading. So in this case we read start of A, and we are here, and we are positioning in these two pumping points. Then we can read the start of these two tokens. And here I show you that the viewpoint can evolve in different ways. So we can choose that the start of this token effectively makes us going from here to here in the blueprint, or we can choose to ignore that and read the other one as well, or we could read both of them or none of them. Okay, these are just two copies. Okay, and then we can go on in this way. Okay, so the evolution is this one. So this is the main core object that is underlying the construction of the automaton, and it is the core object that allows us to construct the automaton. So you see that automaton states are sets of viewpoints, and you see that a viewpoint can split like in this way. So non-deterministically we can choose in which way to make the viewpoint evolve when we read the word. Okay, so this is a split between a single viewpoint that splits into different ones. Okay, and
1 minute, Nicola.
Yeah. It's the last slide. So, and the two viewpoints can fuse if past details of their evolution do not matter anymore. Like in this case. In this case, we choose to have to read the world in different ways. But when the automaton reads this point, the two viewpoints are the same, because it doesn't matter anymore the past the past occurrences of the world. Okay, so blueprints, of course, must match when the trigger of a rule is encountered. So here we encounter the trigger of the rule, and from this point on, the blueprints have to match. Otherwise, the automaton rejects the world. And the final states are those with only completed viewpoints. So this is the core idea of the automaton construction. Then we have p-space hardness proof, which is kind of simpler, and we prove it by reduction from the emptiness problem of the product of n finite automata. And so to conclude, we prove the complexity of qualitative timeline-based planning. The proofs are based on automata theory, and we are also refining the concept of blueprints as introduced in previous work when we prove the complexity of the general setting. So the proof refines that proof by refining the concept of blueprint to this particular qualitative setting. This also sheds light on how such a high complexity problem can be solved so well in practice, because it turns out that most of the one exponential blow up in the complexity of the general setting is indeed caused by the numerical constants. This could be maybe it's not surprising, but this also sheds light on this question. And in the future, as the future work, you may ask whether other easy or easier fragments exist. Maybe some NP complete fragment may be isolated, or if the language can be extended to a not more complex problem. So if the language can be extended while maintaining the complexity at p-space. Thank you, and this concludes the talk.
Thank you for your nice presentation, Nicola. It is also the last talk of the session, so we can go on asking questions for an hour if you want. Yeah, is there any question? I was wondering, Nicola, how far away, if you're working on, how far away you are from an implementation, working implementation of this?
Well, we are not focusing on that kind of the issue. I mean, the working timeline-based planners are well quite developed. These are all the names of the systems. So Europa, for example, or Aspen. Aspen is being used by the European Space Agency in collaboration with NASA to plan the scientific measurements of the Rosetta space mission, which landed the rover on the comet some years ago. So these are very quite well-developed systems. We are rather focusing on the theoretical aspects of this language, that these kind of languages which have been developed quite well on the practical side with software systems, well-developed software systems that apply this kind of paradigm, but there was no a lot of theoretically well-grounded research on the paradigm, and this is in contrast with PDDL, for example, which has its origin in strips, which is based on formal logic from the start. So this is our focus rather than on the implementation.
Great. Well, if there are no other questions, then I would say the session is concluded, Alessandro.